Today we finish up our discussion on both the reproductive and the endocrine system at the same time. As I alluded to in other lectures, so much of reproductive physiology is hormonally and endocrine driven. So as we go through this particular section, we want to make sure we still know all the relevant anatomy, at least as is discussed here now. And that's going to include the function of any particular cells that will be part of the male and or female reproductive systems. We also want to understand the feedback mechanisms involved. We looked at one particular feedback mechanism when we did hormonal feedback, and we particularly isolated out the thyroid gland. We wanted to emphasize that we see a three-tier hierarchy of control, with the hypothalamus being a controlling gland over pituitary secretions. The pituitary, in turn, often will turn around and have a controlling function over another tier of glands. Now, in this case, we picked the thyroid gland because it's one of the most straightforward ones we could present, and it's also one of the more commonly familiar hormonal imbalances. So we get this excitatory cascade stimulating the secretions of any lower gland, and then in turn, as we see an increase in our end hormonal product, we get a negative feedback inhibition to previous glandular tissues, turning off the stimulatory effect on the third tier. Now we see two other examples of a very similar negative feedback pattern in both the male and the female reproductive systems. We want to emphasize those to give an idea on how much more sophisticated the system we see on the screen right now can actually get. Again, we pointed out the thyroid gland first because it was the most straightforward. We wanted to make sure we remember what negative feedback control actually refers to. When we look at the males, we definitely see a step up in sophistication. We still see our hypothalamus, we still see our anterior pituitary, and we still see our end organ glandular tissues, in particular the testes. However, you can see where we're getting more sophisticated here immediately when we have two secretions from the pituitary at the same time, influencing the secretions of two different cellular activities within the testes. In the seminiferous tubules, remember we had our very primitive cells out on what we would consider the superficial aspect of the tubule. Here would be the lumen of the tubule, and we witness a maturation of the sperm from the primitive cells towards the lumen of the tubule, and essentially what we see are sperm ejected from the wall of the tubule and deposited inside the lumen. We see two different cells drive this production. First of all, we need testosterone. Testosterone are going to be secreted by here's labeled interstitial cells, but really you're going to see them more so labeled as Leydig cells on most of the resources you look at. We need testosterone secreted from these Leydig cells to drive sperm maturation. What helps this process occur at a heightened rate is our sustentacular cells, or otherwise known as Sertoli cells, secreting a protein called the androgen binding protein. Now, testosterone is an androgen. So if we have high levels of ABP, androgen binding protein, it is going to bind to testosterone that's been secreted and effectively increase the concentrations of testosterone to drive somatogenesis harder. So we had mentioned we would see examples of hormonal pairings where they support each other. Symbiotic relationship. We see an example of it here. We see gonadotropic releasing hormone secreted from our hypothalamus, dumped into our hypothalamal-hypophyseal portal system, increasing the secretions of both FSH and LH from their anterior pituitary. FSH triggers our Sertoli cells to increase secretion of ABP. LH increases our Leydig cell secretion of testosterone, which will bind to our ABP and drive somatogenesis at an optimal rate. At the same time, we still do get negative feedback because that's still what this entire mechanism is all about. Well, we get two different approaches to that. The testosterone that we saw driving spermatogenesis does go back to actively inhibit LH and FSH secretions from the anterior pituitary, as well as gonadotropin-releasing hormone from the hypothalamus. But we also see inhibin production and secretion to further inhibit FSH and LH from the anterior pituitary. Now, this diagram obviously has a lot of anatomical sketching on there. If we look at a different diagram that's slightly more feedback schematic-esque, we see the same kind of format. We have our gonadotrophic hormone driving the anterior pituitary to secrete LH and FSH. Now we get to see the sophistication drawn out just a little bit more clearly. From the anterior pituitary, we get two separate secretions which target two different cells within the testes. The Sertoli cells will secrete inhibin, active feedback to the pituitary, negative feedback. Remember, it's also going to produce and secrete ABP to bind to the testosterone secreted from our Leydig cells to stimulate that spermatogenesis. That same testosterone goes back to actively inhibit the hypothalamus and the anterior pituitary secretions. So increase in sophistication. We've got more hormones at play here. We got two different hormones coming from the anterior pituitary. We got two different hormones involved in our active inhibition. But we also get a stimulation effect from one of those hormones on one of the testes tissues as well. Now, when we look at the feedback mechanism in the female reproductive system, we kind of have to look at that process one more time, or at least a little bit clearly. Remember, when we look at the female system, it's a cycle. The spermatogenesis is going to be somewhat of a consistent production. And we will see slight rises and falls in our inhibiting hormones, just like we saw with that slight variability with thyroxine in our simplistic model. But when we look at the female reproductive system, we actually have new tissues appearing as we go through our maturation process. We actually break down our 28-day cycle into three phases. First, we have a follicular phase, where we're witnessing the maturation of the follicle. Now, on the diagram that we looked at previously, that's going to be the transition as we go from those primordial follicles through the primary, the secondary follicles. We get to our Graafian follicles. Now we've got a mature follicle ready for ovulation. This is our follicular phase. And it's important to note that that tissue is maturing as we go. If we witness the hormonal levels during that phase, we see LH and FSH present, but at pretty steady levels. We see estrogen. We see a little bit of a dip at the beginning, but generally speaking, as those follicles mature, estrogen also increases over that same period of time. driving the follicles even more. The tissues we never really talked about much earlier on was the endometrial lining. During our follicular phase, we are seeing the endometrial lining thicken in preparation to potentially implant a fertilized egg. When we look at the hormonal activities that we're witnessing during the follicular phase, we have our hypothalamus secreting gonadotropin releasing hormone, triggering the anterior pituitary to secrete LH and FSH. So far, the pattern we saw in the that is going to trigger our follicles to mature and produce estrogen. Now, this is where the diagrams of this particular system gets a little bit misleading, and to a certain extent, you're probably better off following the description for the logic than looking at the colors of the arrows. Everywhere else, we had active inhibition. Our end product hormone raises and it increases inhibition. In this case, we are seeing our estrogen inhibit the anterior pituitary and inhibit the hypothalamus. It's a red line. It's got a negative sign on it. It's inhibition, right? This is not active inhibition. Estrogen is viewed as inhibiting the anterior pituitary at this point because we aren't producing enough estrogen. Estrogen secretions here are going to be somewhat low. We need more estrogen. So it's the lack of estrogen that winds up being inhibitory to the hypothalamus and the pituitary. We see the estrogen increase endometrial thickness. Now, as those follicles develop more and more and more, they are going to produce increasing amounts of estrogen. The increasing amounts of estrogen now removes the inhibition and increases in excitation, reinforcing hypothalamus secretions. The increased estrogen drives that endometrial lining to thicken even further. And of course, our gonadotropin releasing hormone now increase is going to dramatically increase LH and FSH secretions from the anterior pituitary. And that's exactly what we see during our ovulatory phase, a sharp spike in LH and FSH because estrogen has finally gotten to the point where it can excite hypothalamic secretions. The spike of LH and FSH triggers the ovulation, the mature ovum to be released from the mature follicle. All the while, we're seeing an increased thickening on that endometrial lining. From that point forward, now we're in our luteal phase. Because remember, once we ovulate and we lose the ovum from that mature follicle, what's left behind is our corpus luteum, new glandular tissue. In the other two examples we had, we never saw new glandular tissue getting introduced as part of the chronology of our feedback loop. But because we got brand new hormonal tissue, now we're going to have a brand new hormone at play, progesterone. Once ovulation occurs, we see progesterone increase, which actively inhibits our anterior pituitary, inhibits our hypothalamus, decreases gonadotropin releasing hormone, gets LH and FSH to drop back down to normal levels, which is what we witness here. As progesterone increases, LH and FSH drops back down. And here we see a red line indicating inhibition. This is inhibiting a degeneration of the endometrial lining. Progesterone is going to support maintenance of that endometrium so that the egg that was just released, if fertilized, is going to have a healthy endometrial lining in which to embed. If we don't get that implantation in a certain period of time, the corpus luteum degenerates. It can no longer produce enough progesterone. Progesterone levels drop back down. The endometrial lining can no longer be maintained. It sloughs off, and we wind up starting the cycle again by driving the maturation of another follicle to produce another mature egg. So let's just look at those three examples again briefly. The thyroid gland example, simple. 3 glands, 3 hormones, and the level of the end hormone dictates how much active inhibition we get at our 2 higher tier controlling glands. The more thyroid hormone we have, the more inhibition we see at the hypothalamus and the pituitary. Again, this is as straightforward as negative feedback gets when it comes to hormonal control. We stepped up the sophistication when we looked at the male system. From the anterior pituitary this time, we have 2 different hormones at play, influencing 2 different target cells. Each of those target cells produced an entirely different hormone that went back to actively inhibit those higher 2 glands. However, one of those hormones stimulated the other cell in the same gland. And in this way, we get the same fluctuations that we saw in our thyroid system, but still an optimum driving of the rate of spermatogenesis. And then because of the chronology of the 28-day cycle in the female, we get a much more sophisticated negative feedback system apparent here than we saw in the previous 2 examples. One, because some of our inhibition is not active inhibition, it's passive inhibition. I've used this analogy before, but if you're driving along the interstate in a car and you want to slow down, putting on the brake would be active inhibition. It's an action giving you the result you're looking for. Passive inhibition will be the equivalent of just simply taking your foot off the gas and letting that car slow down in a passive manner. Here we see inhibition to the pituitary and the hypothalamus simply because there's not enough estrogen to stimulate. The lack of being able to stimulate by default gives us an inhibitory state. Once we are able to increase the estrogen, because the follicles have matured over that period of time, now we get enough to get a stimulatory effect, giving us the spike in LH and FSH that we need for ovulation. Once ovulation occurs, now we've got a thickened endometrial lining that simply needs to be maintained, and we start producing progesterone that actively inhibits the hypothalamus and the pituitary so that we don't get LH and FSH secretions that might drive a secondary ovulation quite yet, not until we've determined what's happening with the first mature ovum we've released. So again, we have to know the structures. You have to know the functions of the hormones that we're listing here. So as far as structures, corpus luteum, Sertoli cells, Leydig cells, different follicular tissues. And we have to know the feedback mechanisms. And as usual, if we have any questions, please let me know. But this brings us to the end of our endocrine and our reproductive systems now. Take care. Thank you.